Good evening. Can everybody hear me? Cool. Thanks, Lucifer. Okay. Sorry about the slight delay. I was just getting my stuff set up. Alrighty. So. I always get nervous when I kick these things off. Alright, so thanks a lot for all those who have decided to show up and listen in. I've got my wife in the background. I think she's probably going to find what I've got to say very amusing. So if you hear laughter, I'm sure that's coming from her. So today, what we're going to do is we're going to look to own something that appeared on ExploitDB recently. It looks like a fairly lame internet sharing proxy app thingy, and I decided to do this because rather than working on a synthetic challenge, I thought it was about time we did something that was real world. And even though you can argue the Capcom driver thing was real world, it was pretty trivial. Exploiting a backdoor is not exactly difficult. So anyway, I decided what I'd do is I'd pull this down, we'd get it running on Windows 10, and we'd try and own it. And given that there's an exploit out there, it's pretty obvious that it's going to be ownable. As you can see on screen here, EDB's actually verified it. So this particular exploit, which I haven't looked at, is functional. So what I have done is I've downloaded the application to my virtual machine, and from there I'm just going to go through the process of installing it and seeing if we can actually own the thing. So for those of you who are watching, as per normal, sing out if you have questions along the way. I've modded a couple of the usual folks, so hopefully if there's any need for moderation, you guys can help. Greetings, Chumbo, Jardef, Dimitri, Lokifer. Thanks, guys and gals. Should you be gals or guys? Yeah, so ask questions along the way. If I don't explain something very well, then please let me know. So I'm going to start by flipping over to the VM. Alrighty, so as you can see, it's Windows 10, which means straight out of the box we're not going to be able to do anything with executable code on the stack, because Windows 10 just doesn't let that happen. For those of you who have followed along before, you should know that hacking without tea is very uncivilized, so make sure you get yourselves a cup of tea. Alright. Greeting Rezkin and Foob? Yes, Foob. And Got Milk's here too. Alright, enough with the greetings. Let's get this arguably terrible app installed. So I'm just going to get it installed with all the default settings. Accept the license agreement. We'll let it create a desktop icon. Looks pretty standard. And we'll launch it straight up. Okay. It looks like we've got some trialware, which I'm not going to bother reversing. I'm looking to own this thing. I'm not looking to break it illegally by preventing the copy protection from working. So we'll just click try it using the trial version. Okay. Alright, I guess this is it, huh? So it looks like it's got a few bits and pieces of functionality available to it. Now, based on the ExploitDB description and what was actually a Metasploit pull request a little while ago, this exploit was abusing what looked to be a stack buffer overflow in the SOX proxy server. So one would assume that this is the thing that contains the vulnerability that we're going to own. So I'm not going to spend the whole time just like fuzzing all of these things to find it. The knowledge that I have abused up until now will be that this is a vulnerable application and that it's the SOX proxy server that contains the flaw. Hey Prichos. So what I'm going to do to begin with, I'm just going to start this up and see what it does. And click start. Righto, so on clicking start we can see that this is listening on port 1080. So assuming that this is exactly what it is that's vulnerable, I guess we should look to do some kind of interaction with the SOX proxy server. Now, at this point, we're pretty much flying blind, so I don't really know whether or not this requires some kind of abuse of the SOX protocol to make this fail. I don't know if literally I can give it a chunk of data and it will die. I honestly have no idea what to expect. So what I might do is we'll flick back to here and get rid of that. And to begin with, what we might do is just see if we can NC to it, whether or not it actually gives us a connection. I think the IP for this is 56 and 1080. Okay, so there we go. Sending it some data did result in the connection being killed, and the proxy is still running. So okay, so it's probably fair to say that if we did something like, let's see, we always resort to Python, don't we? Let's go with Python, and we'll go print a bunch of times, and we'll just pipe that to NC and see what that does, because you know that's what we do when we do an error exploit dev. So we got back some junk. Didn't really look like anything magic's happened, and okay, clearly nothing's happened, nothing's crashing, nothing's misbehaving, so we may actually have to do some kind of automated, fairly trivial fuzzing. I think what I'm going to do to begin with is act rather dumb, rather than try and implement the SOX protocol, in the hope that that will somehow lead us down the path of something a little more bearable. So what I'm going to do is we'll start writing some Python. There's a good chance that because this thing relies on protocols, that certain characters are going to be interpreted in certain ways. So I think what I'm going to do to start with is we'll just repeatedly connect to it and we'll throw it junk. And when I say junk, what I mean is maybe we can iterate through the key space, the ASCII character set space, and just see if anything falls out. This is what I'd be doing if I was doing a basic manual fuzz. I guess if things get trickier, we can start playing with something like Spike to see if we can actually fuzz it properly. But you know, let's start with the absolute basics. Given the rather rudimentary nature of this, I'm going to start by just importing socket, and I'm going to use socket rather than the pwn tools because yeah, I just think that pwn tools will probably slow things down, and it would be just nice to see interaction on raw sockets rather than having the library sort of mask what's going on. So to begin with, let's create a socket, which I always like to call S. So socket.socket, we want to have a AF inet socket, and socket.sock stream is the type, so that gives us a TCP socket. Next, we want to connect to 10.1.10.56 is the IP, and 1080 is the port that we're listening on. And then later on, we'll probably want to close for the sake of being completely clear. All right, so at this point, we've got a connection. Let's just send it something, and we would start with a times, I don't know, we'll start maybe with 1,000, and we'll close. Now if I run this, which I've already made executable by the way, if I run this, I would assume nothing would happen. Oh, import, command not found. What have I done? Ah, user bin and Python. We better tell it what it is that's required, hey? There you go, watch me fail. Righto, so that ran, and by the looks of it, behaved exactly as expected. Now, what we probably need to do is chuck this in a loop, and as we go, we'll change the character that we're going to be using for each. So let's go for character in range of 0 to 255, so the full ASCII character range. Let's go, I'll call it P for payload. We'll call it, we're going to convert that to a character, so it's actually a character, and from here we'll actually send P times 1,000. Well, probably worth actually doing is saying print currently trying P. Okay, so that'll print out the character, although actually it's probably worth us saying, let's make it a 2-byte hex. And instead of that, we'll call it C. So render the number as a hex rather than actually looking at the character. So that should just dump out everything that we're trying. And, you know, maybe we'll come to something, maybe we won't. Python for loops, yes. Oh, hey, Anti-Snatcher. Good to see you, mate. Yes, I do use Vim. Big fan of Vim. Don't listen to Justin because he's being a troll. Nano, I may have used Nano back in my university days, but it was too elite for me, so I went over to Vim instead. But yeah, I agree. Looping in Python is pretty ugly, but you know, it is what it is. There's not really much we can do about it. Right. So what happens here? Ooh. Oh, this is exciting. So everything seemed to work until we got to character 88. Aha! See? Dumb fuzzing for the win. It looks like that has crashed because of character 88. Okay. Well, that's pretty exciting. So what I'm going to do then instead is I'm going to take this stuff out. Let's do a quick refactor. We'll call this a new function called send stuff. And that's going to send exactly what we give it. Right? We can just leave that. And now outside of this loop, I'm going to exit out early. Import sys as well, so that means I can leave all that other nasty code sitting behind the scenes and it won't get executed. So if we go send stuff hex, was it 88 times 1,000? Yeah, let's just see if that works, right? But what I'll do this time is we'll kick this off. Skip the trial nagware screen and the other nagware screen. Excuse me. And we'll kick it off. Now this time what I'm going to do is I'll attach WinDBG. I would assume that easy proxy is the thing. Yep, that's what it looks like. I tend to have the habit of scrolling all the way down to the bottom of the list and choosing the last item in WinDBG, because that's usually what I've just launched. So there you go. All right, so that's attached. I've disabled symbol resolution on this because with symbol resolution on, it's incredibly slow. And you'll notice I've got this auto command here, .load pykd.pyd. I'll get onto what this is very shortly. PHEW. So when it's not that easy to trigger the crash, what would your next steps be? Try and implement the SOX protocol, then fuzzing fields one by one. That is exactly what I would do, PHEW. I would have a look at the SOX protocol. I would look at the interesting fields, and I would probably look to use something like the spike fuzzer and describe the general layout of the SOX protocol. And I would just say, go ahead and fuzz the fields within SOX. So that's what I would do next. Jardeth, are you sure this bug is related to the exploit you showed at the start, or maybe there's some random other issue with the same software? Great question, Jardeth. Right now, I have no idea. I could be doing the same thing as the original guy. I could be doing something completely different. I'm just going to go with, hey, it broke, and that's exciting. So let's see what happens. So we've attached. I'm just going to run it, and we'll go back to our exploit, and let's see what happens. Okay, we run it. Ooh. Okay, so as you can see, it has actually caused a crash. We've got an access violation. We're just waiting for WinDBG to get back to us on what's going on. I'm hoping it's not trying to resolve symbols, because that'd be annoying. Let's have a quick look. Nope, shouldn't be. So we just need to wait for it to catch up and see what it is that it thinks is wrong. I'm more of a fan of using WinDBG at the moment because, you know, the likes of Immunity, which is handy and nice and a lot of people know about it, it's getting old and you can't debug 64-bit applications in it, so that's why I tend to stick to WinDBG. But if it proves to be continually this slow while we're doing stuff, then I will instead go ahead and use Immunity, because it tends to be a bit quicker for some reason. If the backing track is a little noisy, let me know. I will turn it down. But I did sample this a little bit earlier on, and it shouldn't be too bad. Okay, let's have a look. Rep modest D-word. Okay, so it looks like a buffery overflowy thingy. We check out ED. We're trying to write to EDI. So by the looks of it, EDI, as we can see, is the start of what appears to be a new page. My guess would be that somehow by sending what we've sent, it somehow triggered a flaw in the application that has resulted in it trying to copy too much data to a buffer. And the result of that is we've gone way off the end of our current page, and we're trying to write to the next page. And so that is causing an exception. That's our access violation exception. Okay, so that's a good thing. Based on the description of the original exploit, I mean, it did say that it was an SEH exploit. So perhaps we have actually triggered the exact same code, or maybe not the exact same code, but we've triggered an exploit that's resulted in an SEH. So we should probably check to see whether or not we have somehow managed to gain control of this by checking out the SEH chain. So for those of you who aren't familiar, when you write C or C++ applications and you use structured exception handling on Windows, behind the scenes, when you call functions, some extra metadata is put on the stack at various locations, and the metadata is effectively a linked list, and that linked list contains references or pointers or memory addresses to two things per node. And so when I say node, I mean per entry in the list. The first is a pointer to the next entry in the list. And immediately following that, there is a pointer to the exception handler for the current stack frame. And so what happens is that the exception handlers effectively are chained together up the stack. And so there's pointers to the next exception handler as well as to where the current exception should be handled, so that when an exception is thrown, Windows knows which pointers point to the right areas of memory in order to handle those exceptions. There is a much better description of how SEH works, but for the sake of this tutorial / attempted ownage, it's fair to say that there are 2 pointers on the stack that we are looking to overwrite, and they tend to be quite a bit further down the stack than where our buffers tend to lie. So the question is, how do we determine whether or not we've actually overflown far enough into the buffer to gain control of SEH? Now, there's a few things you can do. Out of the box, there's this exchain function that's built into WinDBG. Now, if we run that, we can see invalid exception stack at address 0. So that's clearly not a valid pointer to a handler of any description. There's another one that I prefer to use, and that comes with a tool called Mona. And Mona is a utility that was written by Peter van Echweten from the Corlan team. The man is a legend. If you haven't heard of him or looked at his material, you should. He is a very inspiring dude, and his material is really good at covering this kind of stuff off. So I'd highly recommend going to have a look at that. You'll find that at corlan.be. Right, so given that says that it's 0, I'm going to go and use the Mona equivalent. I'm going to go pymona, so that invokes a Python extension, and the Python extension was the thing that we loaded just up here, this pykd.pyd. It's effectively just a DLL that taps into the WinDBG library. And from here we can actually, I can just run pymona, and you'll see that here is the Mona menu. So what I'm going to do is I'm going to go pymona. You can go SEH chain or you can go EX chain for the sake of consistency. We'll just do that. So as you can see here, we find exactly the same information. So the pointer to the next SEH handler is 0, and the pointer to the handler is also 0. But you can see here that this gives us a little bit more metadata. It's a good thing. Okay, so clearly we haven't overwritten anything of interest here. So perhaps what we should do at this point is see whether or not we can just throw more data down the neck of our target application. Now what I'm going to do here is get rid of this because we know that we've reached the end. And let's start with our usual approach of having a buffer that we're appending stuff to. So let's go, oops, get rid of that, shove it there. And this time we'll just, I don't know, I'm picking random numbers off the top of my head in the hope that we're eventually going to hit something useful. And we'll go send, can't type tonight, but let's just send the buffer. Okay, alright, so with that set up, all I've done is I've taken the characters that I know cause a crash, and then I've just added some A's at the end in the hope that we're going to go far enough off the end to overwrite the SEH handler. And once we've got control of the SEH handler, then things will hopefully get pretty interesting. So, if you have any questions, again, let me know. I'm not seeing any. Justin's flying the flag for me. Are you having issues with encoding? Is everyone else having issues with coding, or is it better swap it down to low quality? Yeah, sorry guys if you're having problems with download. I haven't had any stalling of uploads. I've had no stalling of downloads on my machine, so I would assume that it should yeah, it should function okay. But yeah, sing out if it continues to be an issue for you. Alright, let's go back to our VM. We'll kick this off again. Try it. Okay, I get the feeling I'm going to be very used to this little rinse repeat routine by the time we get to the end of it. Fire up WinDBG again. Okay, let's do that thing. Oh, here we go. Crashed again, so that's a good sign. But yeah, by the looks of it, we're still waiting for WinDBG to catch up. I'm gonna, after this, I'll try it one more time. If it continues to be a pain in the butt, then I'll flick over to immunity. kids got me for Father's Day. Cheeky buggers. Come on, WinDBG. Okay, so what I'm trying to do, again, while we're waiting for this, is I'm trying to write data to an area somewhere, hopefully on the stack. We know that we've crafted a small payload that causes a crash, thanks to the magic 88 hex character, and then after that I've just pumped a bunch of A's in the hope that it's going to go far enough down the stack to smash over the top of the NSEH and SEH pointers. Get so sick of the nag stream while trying to crack this shit. No, I'm not keygenning anything. That's illegal. We don't do illegal stuff, do we? No, we don't. Come on, DBG. All right. So what we're going to do once here we go. What we're going to do once this is over is hopefully we're going to see that we've got SEH control, and then the fun's really going to start. So let's do our pi mona ex chain. Aha, there we go. Check this out. So you can see that the next SEH and the handler, both those pointers have been clobbered. So that's a bit of a win. It looks like our dumb fuzzing approach has yielded something rather fruitful. So that's kind of exciting. So what does this mean? For those people who aren't familiar with how you can exploit this, as you can see here, this instruction, the instruction that is causing the crash, excuse me again, it's causing an access violation because it's attempting to write to an area of memory that probably isn't mapped. Excuse me. So what that means is you get an access violation, and in Windows land, an access violation results in an exception. So when an exception is thrown, what is invoked to handle that exception? The exception handler. Okay, and what we're saying here is that the function pointer that will get invoked as a result of this is currently in our control. So we have a way of getting control over EIP simply by overwriting the exception handlers. So that's pretty exciting. Clearly though, we have no idea how far into this buffer the next NSEH and handlers are, handler pointer is. So we're going to have to do the classic sort of pattern offset doohickey to figure out exactly how many characters we need to put in the buffer before we get to both of those pointers, and that will allow us to target both of those addresses with something that we can abuse. Okay, nothing, no questions. Dimitri, earlier on today I forced WinDBG to pull down as many symbols as I can for various other things around in Windows, and I've effectively turned off resolution of symbols by specifying no server, and so it shouldn't actually be trying to get symbols from anywhere, but for some reason it's continuing to do so. So maybe what I'll do is I'll flick over to immunity just to speed things up just a little bit this time. So let's launch the app. Start the SOC server off. This time we'll go to immunity. Okay, so attach to easy proxy. Okay, and run. Now watch me fumble with the shortcut keys because in my head I'm using WinDBG, but that's probably not going to work well with immunity. Alright, so going back to our exploit. Now, just so you know, in this folder we've got pattern.txt. This is what I used in the last stream. It just contains 20,000 characters worth of the repeating Metasploit pattern, which saves us from actually having to generate it ourselves. So what I'm going to do here is do our usual I'll call it R for read because I'm lazy. We're going to read from a particular path. We're going to go with open path read as bytes as f return f.read. So I'm being lazy and I'm reading the entire file into memory in one chunk. Here I know that I only need 10,000 characters on top of the 1,000 that we've got for the hex 88. So what I'm going to do is we'll change this up so that we've got we'll have a pattern array, which I will load by going pattern equals read pattern.text. So here we are reading the patterns completely into an array, and then here I'm only taking the first 10,000 characters of it. So that means we'll end up with the first 1,000 being hex 88s, and then the next 10,000 will be our buffer of repeating characters. And so from there we should be able to determine exactly where along the way these the characters sort of fit within those two memory addresses, and from there we'll know exactly what the offsets to those locations happen to be. Foo, how's that music genre song called? I'm playing a guy called Guy Baroni. I believe he's Italian, and he's on SoundCloud and has some really nice tunes and vibes. So I find myself listening to him for this kind of stuff fairly regularly. So yes. Anyway, let's run this and see what happens. Go back to our VM. Okay, so here we go. We've got our access violation as we did before, and we can use our Mona command slightly differently in here because we don't have to load the Python extension. Let's just see what the ex chain has in it. All right, check this out. So we can see here the record smashed at offset 30, and this is one of the reasons why I really like Mona. So you can see 30 characters in into the pattern is exactly where we need to stop, and from there we can start writing the next SEH record and the handler record. Mona is great because it actually does the pattern offset match for you. So what I'm going to do is I'm going to validate that. Let's see if we can just hit the restart. Yeah, restart. Whoops. Nine, there you go, I've already done it once. Okay, so app's running, try it. Start the proxy off. Okay, so that should be ready to go again. Let's go back to our exploit. So we know that the NSEH offset is going to be, it's at 1000 plus 30. So we've got the original 1000 here, followed by 30 into the pattern. So I'm going to leave that like that because I like to keep totals, running totals as I go. I'm interested to know just how many 88s we actually do need, but for now I'm not going to bother with that. I'm just going to actually what we should do is, yeah, so the NSEH offset is that. What we might do is just say we'll call it the crash count equals, we'll call it 1,000, and because we may just adjust these values individually. So what I'm going to do here is change that to crash count, and then here we'll fill it up with A's, but we're only going to be doing it for NSEH offset minus the current length of the buffer. This will allow us to fiddle with things along the way, and the counters should just match up. Let's throw BBBBB. This should go into NSEH, and that should go into the SEH, the next, the SEH handler pointer. And just for the sake of visibility, let's throw a few D's after it so that we can see what's going on. So to recap, we're going for 1088s, followed by a bunch of A's leading all the way up to an NSCH record. Then we should see BBBB, followed by CCC, followed by a bunch of D's. And these two values should appear in NSCH and SCH respectively. Let's kick that off. Back to the VM. This is looking good. And run our EX chain thing again, and bang, there it is. Right, so thank you, Mona, for giving us exactly what we were looking for. Next SCH record is filled with B's, and the SCH handler pointer is filled with C's. Okay, so it's been a pretty simple ride up until now. The problem that we've got though is, as you can see, the address here is 05C6FF78. What I'm going to do is I want to look at the memory map. 05, what was it, this one here? Oops. Yeah, it was this one here, stack of a thread. So as you can see, we've got our own, we've got a thread running. We can see that the access permissions, oh man, I've done it again. The access permissions for this are read write. So that means, as we expected, that we can't execute code on the stack, and that's a classic Windows 10 protection. I don't even know whether you can turn it off anymore, to be honest. No, Justin, it's not. That would have been pretty funny though. We wouldn't have actually got a crash if that was the case. Yeah, so as we can see, we're on the stack. This is the memory address region that we're currently operating in, and it's read write, which means straight away we can't do the classic approach to owning applications via the structured exception handler. So in a classic sort of sense, when dep was not a thing in Windows land, at this point what was possible was you could overwrite the structured exception handler pointer with an address that points to a very, very small gadget of like a 3 or 4 byte set of instructions, which would allow you to easily pivot control back to an area of memory that you know happens to exist and that is controlled by yourself. So when an exception's thrown and handled, what happens is that the stack pointer is kind of thrown through the roof and a bunch of magic stuff happens. But at the point of execution of the handler itself, on the stack you have a value you don't care about. Immediately under that you have another value you don't care about. However, the third value down actually points directly back to the NSCH record, which immediately precedes the SCH record that you overwrote in the first place. So if you were able to find the address of any executable area of memory that contains what most people refer to as a pop ret. So pop a value from the stack into any register, do the same again, so you skip the first two, and then when you call ret, that returns control directly to the NSCH record. So what I think we might do, even though we can't abuse that, we might still give that a crack, just for the sake of demonstration. So from there, we'll take the next step of trying to ROP this up. Okay, so this is where I need to add a quick disclaimer. I knew that using Mona to generate ROP gadgets can sometimes take a very, very long time. So earlier on today, I installed this application on this VM, attached to it, generated ROP gadgets, detached from it, and exited it and removed it from the machine. So you'll be pleased to know that saved quite a substantial amount of time that I didn't want to have you guys sit through for the sake of the stream. But it does make it kind of sound like I've looked at this before when I haven't. I can promise you all I've done is generate ROP gadgets so that we didn't have to do it now. Anyway, so now what I'm going to do is I'm going to use Mona. Again, you can see down the bottom left-hand area of this screen. I'm going to use Mona to generate or scan the current application for SEH related records. And what this is going to do is it's going to look for pop-pop-ret gadgets all over the place. So this is a baked-in feature. Let me show you. So you can see just here. Find pointers to assist with SEH overwrite exploits. So that is the classic pop-pop-ret thing. All right, so we're just going to go Mona SEH. It can sometimes take a little bit of time. Let's go back to the log window. So there's, as you can see, there are 642 pointers, many of which start with null. I get the feeling that null's not necessarily going to be a problem though, but that remains to be seen. What I'll do is I'll go to the logs folder, which I set up earlier, Mona logs, easy proxy. Now you can see here earlier today, all of these things here, except for the SEH, I actually generated earlier today so that we didn't have to do it now. It was a very long wait, so you'll be glad that I didn't. But this is the file we're interested in, is the SEH file. We can see here that there really are quite a few pointers in here that do all kinds of magic, wonderful stuff. And each one of them, as you can see, they have pop into a register, and then ret. Okay, in each one of these, as you can see, page execute read. So we know that we can actually execute the code. Notice as well that this binary is not compiled with safe SEH, which is a bit of a fail. So I'm just going to randomly pick this address here, right? And I'm going to use that as our SEH record. So let's call this PPR address. So that's pop-pop-ret address. What am I doing? Paste. There you go. So what I'm also going to do is import struct, and I'm going to have a really lame p32 function which takes a value and returns struct.pack, whatever the value is, and that means I don't have to repeat struct.pack all over the place. So what we're going to do is we're going to replace this SEH record with p32 of the PPR address, and from here, because we, like I said, when we pop and ret, we should see this bit of code here attempt to be executed. I'm going to leave it as BBBB for now. And then what I'm going to do is we'll go back to Mona. I'm going to restart the application again, given that we're sort of at a crash point that's not useful to us. Fire up the app. Kick off the proxy server. PHEW. Yes, that's correct. If null bytes are considered a bad character in this scenario, we wouldn't be able to use that address. That is exactly correct, yes. All right, so now what I'm going to do is I'm going to pause pause execution, and I'm going to go to, oops, there we go. That's not what I'm looking to do. Let's go back to the address that we chose, and we're going to jump to this address here in memory. As we can see, there's a pop-pop-ret. I'm going to shove a breakpoint just there at that instruction. So this, if this works, what will happen is that we'll be able to pass the exception to the application, have it handled, and because we've specified this address, we should actually get a breakpoint. We should actually get a debug break happening at this exact location, assuming all goes well and we haven't got bad characters in here for some reason. So let's keep that running. This will allow us to actually look at how the stack is arranged while we're doing our thing as well. Okay, so let's just quickly double check. We've got our crash count of 88s, followed by a bunch of A's, followed by B's, followed by the address of the pop-pop-ret, followed by some D's. Let's do this thing. back to the VM. Okay, so what we can see here is access violation. So we can execute, or we can go Shift F7, F8, F9 to force the application to handle the exception. But before we do that, we're just going to have a look again at the EX chain. Alright, so as we can see, the handler does actually contain a pointer to what we've got our breakpoint set on. So let's now pass control. Aha! Okay, excellent. So execution has paused at our breakpoint. And so what that's told us a bunch of stuff. That's told us that nulls are not bad characters. That's told us that we know exactly where that exception handler is in memory, and that we've been able to overwrite everything that we want to overwrite up to the point where the structured exception handler pointer exists. We've specified an address to a pop ret, and when passing the exception through to the application to handle it, we can see that the value we have given it is actually being executed. So this means that we have now managed to get control of EIP. Now, if we just have a look, we can see that at the top of the stack here on the right hand side, we've got a pointer that goes to NTDLL somewhere, which we don't care about. We've got another pointer which points some way down the stack. But in third place, we can see B. This is the thing that we control. Okay, this is exciting. So let's just quickly, we'll step one by one. Let me just quickly check what the shortcuts are again. Debug, step into F7 and F8. Okay, so I'm going to hit F7, and you can see we've popped a value into ECX. We're going to do it again. And here at the top of the stack, a pointer to FF78 is sitting there ready to go. And so when we call ret, what happens? Look at that. EIP now points directly to the 4 bytes that are BBBB, and that is something that we control. Like if are we able to scroll up? Let's see. Look at all this. These are all the A's that we control. So we have passed control now directly into the buffer that we control. So as a result, if we didn't have non-executable stacks enabled, i.e. back in the days of Windows XP, right now we could literally do some very simple shell coding and we would have shells. However, you'll notice that when I press F7 again here to execute the next instruction, it should fail. It doesn't. And that's probably because of the debugger. That's interesting, isn't it? Let's pretend that it did actually fail. Let me just have a quick look at the memory protectors again. 5D0FF7C. 5D. There it is. So according to this, it's only read and write, but I'm calling bullshit on that. I reckon if I did that outside of this application, it wouldn't. Outside of the debugger, it probably wouldn't work. If I did the same thing in WinDBG, I'm guessing it wouldn't have worked as well. But that is, I admit, this is my surprise face. That should have caused an access violation. What's going on in the chat? Justin's helping me out, is he? Oh, there's quite a bit of back scroll here. Null bytes. Okay, might be a way depending on some conditions. Boj has time. We should chat about it. Yeah, we can talk about how we can do that at the end of the stream if we have enough. So that's a question around how do you bypass things like invalid characters when you have null bytes at the beginning and null bytes invalid. So we can talk about that a little bit later on. So something to do with add and sub, not at this point, Food, but there are a number of different things that we can do. We can talk about that a little bit later on. Greetings, the Fridge Master. Thanks for coming along. Right. Now, despite the fact that that appeared to work, I'm going to assume that that is not the case, and that I shouldn't be able to do any form of execution of something on the stack. Instead, I'm going to assume that that did throw an access violation, and we are going to go ahead and rock. This is where it's much more fun, and we know it's going to be more universal for when things like dep are actually enabled. Okay, so our plan at this point is we want to find a way of gaining control of EIP, which we have already done, and then from there actually force the application to execute our code despite the fact that the area of memory that we're able to write our code to is not executable. Okay, so for those people who didn't see the last stream where I discussed ROP, at least on the Linux side, the principle is pretty much exactly the same. We are able to send data to an application, but we're not actually able to mark it as executable up front. And so as a result, the only areas of the application that we can execute are the ones that are currently already marked as executable. So the canonical example is that which runs the application. So we can see here, for some unknown reason, each one of these sections here, this one in particular, the code section, is originally read and executable, and for some reason at the moment it's read-write executable. I wonder if that's something to do with the application itself, or whether it's the debugger. I hope it's the latter, because that would make me very sad. But as you can see, there's a bunch of other read-write executable stuff going on here. Let's just pretend we didn't see that. So what we're going to do is we're going to work on the assumption that the only code that we can execute is code that lives inside this code section here. And from here, what we need to be able to do is say, okay, if we're able to get control of EIP, we want to make it so that the instructions that are executed inside the application are going to work together to allow us to do something a little more nefarious. Yes, sorry Justin, you are right. It was originally read-write executable, and now it's only read executable. You're right, sorry, I had my columns the wrong way around. So that would have happened during segment loading, section loading, etc. Now I've just noticed a very small issue with streaming. Are you guys still able to get to the stream okay? Oh, look at that, OPSEC failure. Righto, so what I'm going to do now is I'm going to give a quick overview, a quick view exactly of how the mechanics of ROP actually work. So again, I did do this last stream, and I'm going to quickly cover it on this stream as well. The first thing that we need to do, one of the key differences between this kind of exploit and the one that I discussed in the last stream, is that when SEH handling occurs, ESP is shifted to a very different area of the stack, and a bunch of other registers are cleared. Okay, so if we go back to the CPU view, you can see EAX is cleared, EBX is cleared, ESI is cleared, EDI is cleared. So all of these things that we may have had control over before are magically cleared. They're cleared because they the intent is to protect. It's intended to protect the computer against exploitation. That's effectively what it's about. So when an exception is thrown, a bunch of registers are cleared, and that kind of makes things a little more difficult for us in this scenario. However, there are still other things that we can do, but the biggest problem that we have, and I'm going to have to demonstrate this again just to show you. I'm going to restart the application, get it running again, try, okay, start the proxy, and then we're going to launch our exploit again. Run the exploit, get our crash, just make sure that where are we? Check our EX chain again. I'm just going to make sure that I've set up a breakpoint at this address, which I should just do by copying this again. back to the CPU window, go to the address. Okay, so the breakpoint's still set. Now what I'd like you to pay attention to at this point is this. ESP, the current value of the stack pointer is this. So what I'm going to do is, there you go, that's what the current stack pointer is. Now the reason why I'm mentioning this is because I really want you guys to see just how far the stack pointer moves when an exception is handled. So let's go back here. Okay, so I skipped over it, exception's been handled, and now let's have a look at ESP. Take a copy of that, compare it to this. Well, in this case, it's actually nowhere near as bad as I have seen in the past, but you can see here that we've gone a fair distance. By the looks of it, just as a ballpark, it would be what, hex 6, 7, 8, 9, A, B, C, so hex 560 or something like that, 550. So quite a long way as far as the number of bytes is concerned. And so the problem we've got now is, because we can't abuse ret, because we don't have the ability to literally jump to our code in the normal fashion, to abuse ROP, or to use ROP to give us code execution, we need to move the stack pointer back down into our buffer. And so what that's generally referred to as is stack pivoting. So what we want to do is we want to get the stack, which is kind of moved all the way up here, and we want to pivot it back down to an area of memory that we currently control. Now thankfully, according to this, it's not that big compared to what I've seen before, but still noticeably different. What I might quickly do is be lazy and use Google to do some math for me. Because why not? Okay, so 5B. So that's how many bytes we've gone from to. Now we may be in a fortunate position here, because I know that we've already, in our exploit, we've thrown how many characters? 1030 characters. So it might not actually be that much further than that. Or is it? Yeah, it's a couple of pages, isn't it? Is it? No, it's not quite that far. Not even a page. So what we need to do is we need to find a memory address that points to a series of instructions that's going to move the stack pointer all the way back down to where our payload happens to be, and then call ret. Now what happens there is that the address that ESP currently points to is then used to pass control again to EIP, and code execution will continue. Now ESP is very special in this scenario because we're going to use it to execute little pieces of code that exist in memory as it currently stands, to glue together some values in a register, or in the registers for us, so that we can construct a payload that we can later execute, and I'll get into that in just a minute. Does anyone have any questions up until now? I'm not seeing any, and Justin has been doing the thing. No questions yet. I'll keep an eye on them. Righto, so let's take a look at this this folder over here. Now, as I said, I got Mona to generate this set of data for me earlier on today. Now what I'm going to do is show you the help file for Mona. You'll see that there is a ROP function. Now, what this does is it iterates through all the areas of memory looking for things that look and smell like decent, usable ROP gadgets that we can use to glue together. So this is the instruction that I ran earlier on today, and I will explain this in a bit more detail afterwards. But the result of executing that is what we're seeing here. All of these things come out, and what it's done is it's generated a bunch of stuff that makes it substantially easier for us to construct a payload rather than having to go searching for things manually. Now, one of the things that it generates is this stack pivot. Okay, so stackpivot.txt contains a bunch of information. Specifically, a bunch of addresses followed by how big a pivot would occur should this this particular series of instructions be executed. So as we can see here, we've got a pop, pop, ret followed by 12. So that effectively pulls 1, 2, 3, 4, 5, 6, 7, 8 bytes off the stack and then calls ret. Okay, so what we're doing is we're, in inverted commas, pivoting the stack by 8 bytes by doing that. But clearly, in our case, that's not enough. We want to be able to do more than that. So what I'm going to do is I'm going to scroll down. As you can see here, the pivots are getting bigger. So Mona has generated this file, and it makes it super easy for us to look for pivots that are going to be in the ballpark of what we're looking for. Here we go. We're starting to get to some decent sized pivots here. Whoop, here we go. Check this out. Okay, so looking at around this sort of area here, we can see that we've got pivots of hex 424, hex 430, 434, 670. Okay, so now we know, based on our rudimentary Googling, that hex 5B0 would drop us right back at the NSCH, but we know that we've got 1,000 bytes before that. So if we remove 1,000 from that, what else do we get? Oh, look at that, 1C. That's all we need is 1C8. That's nothing. So we could go all the way back up here. 1C8. That would drop us straight to the beginning of the payload. No, it wouldn't. We'd need to get rid of 1,030. Yeah, 1,030 would take us to the beginning of the payload. So that would be hex 1AA. But we don't want to go to the beginning of the payload. We only want to go to the beginning of the A's, don't we? In fact, this brings the question, how many 88s do we actually need in order to cause the crash? So at this point, I'm thinking in my head, we've got a number of 8s we need to render to cause the crash, and then we've got a big buffer followed by the NSCH record and the SCH record. Now, the SCH record is important and we can't muck with that. The question is, do we have enough space between the crash area and that SCH record to sort of squeeze our payload in? I'm thinking what we might need to do at this point, just quickly, is guess. Actually, no, let's do a smart guess. I'm going to rerun the app again. This time what I'm going to do is I'm going to start a loop, and I'm going to keep looping until we get an actual crash, and that'll tell us just how many 88s we need. So let's do another rudimentary set of fuzzing. Let's just launch the app again. I'll hit try it. Let's see what we've got here. Do you need to know how many 88s? Yeah. Yes, Atwolf, that's exactly what I'm going to do. Anyone would think that you guys know more about this than me. Way to go for making me feel stupid. It's okay, I don't need you to make me feel stupid. I already feel pretty stupid. Okay, so we've got that running. Let's do the following. Right, so I'm going to do my 6 exit 1 here again. And 4. Actually, we don't even need 4. Let's start with 1. And then we're going to go while true, because hopefully it will crash eventually. We're going to go, let's see. What do we need? Let's go with send stuff. hex 88 times by C, and we'll throw a bunch of A's on the end. Oops, can't type. But we need to print. We'll just print out C so we know exactly how big it is. So if we do this, what happens? Oh, check that out. I didn't even increment C. I blame you guys for that. Righto, so 1, 2, 3, 4, 5, 6, 7, 8. What's happening here? Why is it complaining? Connection refused. Is that right? Are we actually seeing a... Yeah, we are. We are seeing a crash. Yes, we're seeing a crash. Looks like we only need 8. All right, let's just quickly validate that. Comment that stuff out. We should probably comment that out as well. So instead of crash count, let's go with 1,000. Sorry, let's go with 8, and we'll see what that does. Quickly restart this to make sure nothing untoward is going to cause our exploitation path to fail. Okay, launch the socks proxy. Back and boom. All right, let's have a look at our SEH chain again. EX chain. Is it looking good? Still looking good. It's got exactly what we want in it. All right, this is interesting. So if we go back to the CPU view, and there you go. Would you look at that? We do actually only need 8 of them. How exciting. So if we only need 8, that means 1,030 minus 8 is where we could actually start putting our ROP chain together. If we go back to Chrome, there you go. So we need a pivot of hex 1b2, and that would land us back in an area of memory that we control. That would land ESP, I should say, back in an area of memory that we control. So let's go back to stack pivot. What do we need again? We need 1b2, 194, 194, 1c8. So 1c8 is the closest we're going to get, right? Which isn't that much further. What is it? Hex 16 further. Yeah? So, if we go back to here, what we're going to do is we'll put a marker in here that says, we'll call it ROP start is, I fail at math. So that's what our actual thing needs to be. Sorry, it's 1c8, isn't it? 1c8. Got to get my math straight in my head now. If it's only 1c8, that's going to be... I'm failing. Someone think for me. 1b2. So it's hex 16 past the end. Hex 16 past the end of crash count. Right? So from here we should be able to go fill the A's up until the where are we? ROP start. Then what we'll do is we'll fill with B's up through to the NSEH offset. We'll fill the NSEH with C's. NSEH at this point actually doesn't matter. We're not really going to use it. It's just this address that matters. So we should have 8 hex 88s, and we should have a bunch of A's that take us up to the start of where we're going to put our ROP chain. followed by the area of memory that should make up our ROP chain when we've actually constructed it, and then the usual shenanigans left at the end. Okay, Justin, what are you asking me? Are you sure we don't only need one? Don't only need one what? Justin? Let's just find out what Justin's asking. Only need one what? What is it that you're looking for? Crash count x16. While you're answering my question, I'm just going to go and grab this address that we decided on, or one of them. So this one here maybe. Let's have a look. We've got a few to choose from. Oh, I like this one. This is very simple. Just add ESB followed by written. Yeah, couldn't get much more trivial than that. Ah, right. Okay, sorry, Justin. Yep. Thankfully, we've moved past that. All right, so I'm going to call this pivot address. There it is. Yeah, you might be right. Actually, we may only just need one, but yeah, we didn't. We just seemed to do it 8 times and it failed. So yeah, you might well be right. But given what I'm seeing, and I know that I've got to pivot down to 16 anyway. Let's sorry, 16 hex 16 plus 8, which takes us to what, hex 26? No, I can't even do math. 6 and 8 is 12, it's hex 1c. We would still want to go a little bit further than that. So I'm hoping what we're seeing here is, instead of this PPR address, let's just comment that out. We're not going to do PPRs anymore, we're going to do the pivot. And we want the stack to pivot appropriately. In order to do that, we should set a breakpoint. There it is. Set a breakpoint there. We're currently in a crashed state. Yeah, I think we are. Okay, let's restart again. Run the application. How are we doing for time? We're about an hour in, aren't we? That's not too bad. I was a little scared that we were going to be flapping around during fuzzing for quite a bit longer than we actually were. Let's kick the exploit off again. Okay, let's just have a quick look at the exception chain. 29BC7, that's what we chose, wasn't it? Yep, so we haven't stumbled on any bad characters there either, so that's a bit of a win. Back to the CPU view so we can see what's going on, and there we go. Righto. So I'm going to pivot ESP via 1C8. Let's see how good the math was. Clearly not good enough. We're off by a long shot, aren't we? I thought that was a little too trivial. Oh, there it is. Try adding, what, another... Oh, I'm so far off, it's scary. Wow. So I was hoping that we would land here, but as you can see, I am nowhere near it. Sorry, I meant to say, yeah, land just in here. In fact, it doesn't even look like it's functioning as I was expecting. 1, 2, 3, 4. Look, ooh, that's interesting. So we're sending in, yeah, we're sending in 8 followed by A's. I've done something really stupid, but that shouldn't come as a surprise. Hex 16, yeah, of course. That's not a multiple of 4. Anyway, this is clearly way off. So what I'm going to do is I'm just going to quickly rerun that again and redo my math. because I'm a fool. And this time I'm going to take it a little more seriously. Try it. Math is hard, man. I agree. Thanks for making me feel a little bit better about sucking. I appreciate it. I love you guys. Okay. Current ESP is that. At the point of handling, ESP is that. Question is, if we, oops. That was my assumption that ESP was actually where it should be. It's clearly not. It should be this 612. It's even further up. E. There you go. Check that out. That's more along the lines of where I was expecting. Okay, so there you go. You can see that we've actually got a massive difference. That looks like it points to the beginning of the D's. Let's just go and quickly check. It's not even at the beginning. Right, so the A's begin somewhere down here. Alright, so 612 dB82. 612 dB8. Let's leave it as something that is a multiple of 4 at least. Yeah? Alright, so we need to, this is what we need to figure out. The difference between these two things. Alright. Sorry about that. Whew, that's quite a bit bigger, isn't it? Let's hope that we've got something that can pivot as well far enough. So getting bigger, it's getting bigger. Whee! Come on. Ooh, wow, there's some massive ones in here. So according to this, if we added this to what ESP currently sits at, and what is it, 400 BC7? Yep. We need to add at least this, right? We've currently got it at 6. Oh, hang on. I'm being stupid again. Ugh. So that's where ESP is now. And that's where it needs to be. 127. Am I going around in circles? I am. Aren't I? So we're about to change ESP, which points to 6127760, and we want it to point to 612 dB. There we go, that's our problem. dB, let's just go with dB 80, which is what I think I had here, dB. Right, so we need this address, and we need this one. Yeah? That looks a bit better. I meant that, just so you know. Even bigger. I've got a statement in the form of a question that might shortcut the math. Do you want to go down a rabbit hole? Yeah, well, maybe we can talk about that after, mate, but I think what I'm going to do is I'm going to choose one of these gadgets and see where it takes me. This isn't going to be far enough by the looks of it. But let's just double check. So we've currently got, that's our stack pointer. And if we add that, we end up with 612C428. So way too far away. Whereas if we do the next gadget, which is 8360, we get to F9C0, which is a long way away. Wow, we're getting right. F9. So it should be down here somewhere. Doesn't give us a great deal of, oh, look at that. We're already off the tail end anyway, right? So it looks like we don't have a great deal of space to shove a rock chain in there, does it? That's a shame. Okay, so what we're trying to do, just to replay what we were talking about before. Hello, Switch. What we're talking about before is we know where ESP currently is. We want to move ESP so that it lives somewhere inside the area of memory that we control. And at the moment, that's proving to be slightly tricky because the gadgets that we have available to us allow us to either go way too far or not far enough. I'm going to start by doing the not far enough option to begin with, and we'll take it from there. Maybe we'll stumble across something that I'm missing in the process. Yeah, one before C428, it's way too early. Another option for what we have here is to look for things like this. So what we could do is, if we have a look at this, you see that this is a pointer that points down to an area of memory that we control. So if we were able to just pivot and then ret to this, then that would be a different. What we would need to do is sort of pop all of this stuff off and then pop ESP and then ret. But unfortunately, we don't have the ability to do that. Let me just quickly have a look at, I wonder if there is a pop ESP ret. So just bear with me 1 second. Now the reason why I'm suggesting this, you know how we originally had our pop ret gadget. Now we can pop the first two off and then we return. So that pointer actually points to the NSEH records. So what I was thinking is if we can go pop ESP, what that means is it takes the pointer to NSEH and drops that into ESP, followed by a ret, which pivots the stack straight back down to where NSEH happens to be. So what we can do is there is a feature of Mona called find. Here we go. Find wild? Yep, find wild. So we can go help find wild. What does it do? One more of the following global options. Find instructions in memory. So here we go. That's exactly what we're looking for. We can go call find wild and give it pop. Is it pop star? Actually, let's just go with pop ESP followed by ret. And we'll do that in the easy proxy module only. Oop. Back to the log window. Okay, so you can see we've got a few pop ESP options, but we need a couple of other pops before it. So I can't remember that. I think it's just pop followed by a wildcard like that. Let's see what it does. There you go, no pointers. So we can't take that approach, which is a bit crap. Let's just see if that works. Oh no, that's not the syntax. It's a question mark. No. Let's have a look. Since you use numeric offset wildcard, a single, whatever. Be interesting to know exactly what these wildcards actually support. Ah, R32, any register. That's what I meant. So we want pop ESP. So if we can go pop R32. Oop. Thought it crashed for a minute there. There you go, that's more, I'm more likely to trust this result. Found a total of 0 pointers. So we can't really do a pop, and ret. Pop, ESP, ret. So we're still kind of stuck in that area where we can pivot too far or not far enough. Based on the math that I'm seeing here though. So if we go forward, I know I'm gonna have to go at least that many bytes. So what I'm gonna do, just for shizzles, let's just shove this into, instead of ROP start being that, we're going to go and set it to that. Okay, so we'll leave everything else there. And instead of going that many Ds, we're going to go to, I'm going to change that so that ROPs, we specify ROP start times, minus, I should say, not times. So what I'm doing there is we're going to go all the way to the SEH record and overwrite, and then from there I'm going to write Ds all the way to the end, or I should say right up to the point where I think the ROP gadget would begin, or ROP gadgets would begin, and then let's write just 4 E's at that point, followed by some Fs. We'll just do 100 of them. And then what I'm going to do is try and land our ROP just there and see if we've got enough space to play with. Okay, now our pivot address is going to change. We're going to be using a big pivot. We're going to be using one of these. So it's 360. They've all got ret and 4s. That's not really much we can do about that. So we'll just choose the first one and hope that it doesn't have any bad characters in it. Ah, okay. Sorry, Justin. Yeah. I'm sorry that I didn't listen to you when you quizzed me on that in the first place. But yeah, pop ESP ret is another way of doing it. But yeah, from what I can see here, there doesn't appear to be a way of doing it unless I start sort of scrounging around for gadgets that kind of do arbitrary crap along the way, or munge ESP in some other way, or there's other sort of interleaved instructions in there that will do other things that are effectively NOPs but still allow us to pivot in the way that we would like. But yeah, you had a valid question you'd like to chat about if we have time. Sure, mate, if you add it to the list, we can definitely cover that off. Okay, so this is going to be our new address. So what I'm going to do while I'm standing at this point is chuck another breakpoint here. Interesting that we go back to our gadgets here. It's got move dword pointer ECX. Now we don't actually need that. That doesn't do anything. All we care about is this. So I'm not going to use that address. I'm going to use this address. Right? Which is 38 instead. Righto, so let's go back here. And 38 is going to be our pivot address instead. Alright. So that means we're going to pivot directly to the add ESP, whatever it is. Alright, quick rinse repeat. Get our debugger running again. I must be boring because I'm losing viewers. But that's okay. Righto, so fire up our proxy again. Start. Run our exploit. Let's see what happens. Okay, on the plus side, it doesn't look like anything has changed. By the looks at least. So at the point of our exception, minor ex chain. Ooh. I've made a mistake, haven't I? We now have A's smashing our buffer. What have I done? Oh, that's the problem. We don't need ROP start in our chain here anymore, do we? We've already gone way too far. Let's just make sure. Yeah. Sorry about that. So what had happened was I left one set of one instruction in there to smash the entire buffer with A's up until ROP start, and because we changed that value, it was no longer valid. Okay, let's try that again. That looks a bit better, doesn't it? There we go. Much better. Alrighty, back to CPU view. Let's pass control to our ROP. And let's see, when we add ESP to 8360, what happens to it? Oh, there we go. Is it at the beginning of the Ds? Not quite. So let me just quickly go back to our exploit. So you can see we're somewhere in here, but we've clearly gone a little further than I had expected. So let's just see if we can go and follow that in the dump. Scroll. And there's quite a few. Yeah. Okay. So that would mean that if we decided to go with the previous one, yeah, we'd still be nowhere near it. So this is effectively what we're going to have to worry about. So ESP is currently C0, and the beginning of our Ds is at 8. Where are we? 8.2. F82. So we are quite a way off. We need to get rid of this. Where are we? Recommended online self-paced CTFs. I'll let Justin answer that. Hello, Nara999. Thanks for coming. So copy that current address to there. So that's what ESP is currently. And we thought it was going to be F80, DF80. Yeah, which actually makes sense because we did our math wrong, didn't we? Just quickly go back to the Chrome calculator. So we need to add another that to our exploit. Oh no, I've gone too far, haven't I? No, I haven't. Yeah, I have. So that needs to be minus this. Yeah, so going back to here, we can see we're way too far down in the Ds. I thought that our chain would have started at at the E's. That's where we thought our thing would begin. But it didn't. It was much further up. Ooh, hang on here. This is interesting. Check this out. Well, this would explain why. It looks like... Does it? C90. Okay, so let's follow this in the dump as well. Scrolling down, we get to the end of the D's. It looks like some magic stuff is being copied over the top of the tail of our payload. Isn't that fascinating? Ah, this is the copy that results in the exception happening in the first place. Right. So at a certain point, we get to we get things being copied from the top down to the bottom. We can probably abuse this in some way. But the important thing to note is that F9C0, which is in just here, is where we're currently landing, right? So we just need to target that specifically. This might actually be a little trickier. So what we might have to do is the pattern offset trick again to figure out exactly how far we need to go. So what I'm going to do is get rid of this, and let's do our pattern. And this time we're going to add, well, we know that ROP start is going to be far enough, yeah? So let's go with ROP start minus len of buff. So based on what we had before, that should actually give us some idea of how far down the chain we need to go. So let's do that. Okay, yes. Restart our application. Go, go, go. Try it. Okay. Start the proxy. Okay. Run the exploit. Right, let's see. Add ESP. Boom. There it is. So, at this point, what we should be able to do is go bang Mona find MSP, because find MSP should tell us exactly how far. Here we go. Let's check this out. ESP points at offset 6718 in the normal pattern. Right, so that's handy, because that 6718 is exactly how far we need to punch into ROP start. So 6718. Let's get rid of that. Let's get this back in, and we'll put D's in there times ROP start minus len buff. Okay. We're now back to E's. Excuse me. Let's just, I don't know, chuck some F's in for good measure. Okay. Rerun. I think it's probably worth moving over to immunity given the speed of the rinse repeat. I probably would have lost it with WinDBG by now. Alright, so we've run our exploit. Let's have a look. Ready? Come on, show us the money. Oh, gone too far. We're nowhere near it again. Nowhere near it. Beginning to wonder if this is actually constantly changing. How far did we go? Oh, hang on, maybe it was hex. That might have been my problem. Well, let's go again. take Justin's advice for sure. Grab some arbitrary binary. It's really good to just pull a binary straight off of the likes of ExploitDB or something that you know has got a DOS proof of concept, or something that has already been owned, and just practice it by yourself. That's what I try and do, at least. As you can see, I'm trying now and really not doing a fantastic job of it. Aha! So, what happened there? Yet again, so we're landing in exactly the same spot, but my offsets are still way out of whack. And I'm wondering, is this to do with copying? Or is it to do with something else? Because that there looks like the address, BBBCC, there you go, that's the address that we gave it, isn't it? Ah, maybe not. The address we have for the pivot is 43AD38. And that is nothing like what we're seeing here. Check that out. How interesting. Okay, so I'm wondering whether or not part of the problem that we're seeing here is I'm changing the length of the payload that I'm sending at each time. And I'm starting to wonder if that's what's causing some headaches. But then again, check this out. That's the valid address that we've clearly gone from. This is all the stuff that we've smashed. You can see back up here is where ESP happens to be. So what I'm going to do now is I'm going to have a fixed payload size. Okay? And what I'm going to do is I'm going to hard code that to something like hex 8000. In fact, no, I'm going to make it slightly bigger, make it 9. As far as ROP start is, I'm going to get rid of all of these again because we don't care, and I'm going to go back to having buff plus equals pattern of payload size minus the length of the buffer. Okay, now from now on, I'm going to make sure that the size of the payload that we are using is consistent across each run, because I'm thinking that that is causing some problems as well. It could possibly be something to do with bad characters as well, but my feeling is that that's not the case, given that the pivot address is functioning exactly as we would expect. So yeah, I'm just going to assume for now that it's not because of a bad character. Okay, let's rinse repeat again, and let's see if our offsets change. Rinse repeat. Kick off the proxy. Run the exploit. And pivot. Okay, let's do the find MSP thing again. Stack pivot. Here we go. Examining registers. 6718 in the normal pattern. So it still says 6718. Oh, I've just figured out what I was doing wrong. Numpty. So that's saying 6718 from the start of the pattern. Right, so that means the ROP start, oops, that's definitely not hex, but here we need to go buff plus equals D times ROP start. Now, instead of taking into account the previous length of the buffer, that is fixed from the start of this payload size. right? That makes a lot more sense. So that means that from here, that is where we should land. Okay, let's put FFFF in there as well. Okay, I'm feeling a bit more confident about that. So what I was doing there was I was using an offset address based on the start of the payload when I should have been doing it based on the start of the pattern. And the pattern was way down in the guts of the payload. So instead of taking the current length of the payload into account while generating it, we're now just doing it as an absolute. There it is. Okay, that's much better. So we're now at a point where when we call ret, you'll see here that E will pop into ESP. Sorry, will pop into EIP, and ESP should drop by 8 instead of 4. There you go. So as you can see, EIP is now pointing to an area that we control, and here's where our ROP can go. All right, we're actually making progress. This is much more positive. Apologies for the fumbling. I hope it was valuable to you. Anyway, so what we can do now is we can do NSEH offset minus length buffer, and we're just going to add 4, and then we can get rid of this. I'm going to set that to A because I like to, and then I'm going to change that to B. This is the start of our ROP chain. Or I should say this is the start of our ROP chain here. And then the next thing here is ignored because we've got a ret n at the end, right? So if we quickly go back here, you'll see what I'm talking about. Our stack pivot has a ret n 4, which basically says when we return, shift ESP down another 4 bytes, and that's got to do with the calling convention, which in this case is most likely, what is it, standard call rather than CDECL. So CDECL says the caller will clean up, standard call says that the call E will clean up, and clearly this function is a standard call function. So that's okay, because what I'm going to do is I'm going to use something called I'm going to find a ROP knock. A ROP knock is literally a direct call to a retin instruction, and the reason why I'm going to do that is because it makes it pretty easy to debug and look at how ESP moves around. So that's one thing that I'm going to quickly wire in, and I'm going to show you how from here ROPing is going to function. I'm going to go back to, I'm going to open up rop.txt, which has thousands of bloody gadgets in it, but we'll get to these later, and look for something really short. Let's just go for, oops. Of course it's not going to do that, is it? I'm trying to find a short ROP gadget like this. Here we go. Pop ESI is a single instruction, which means that there plus 1 will be a ROP knock. Right, so ROP knock address. Now, the word ROP knock is intended to imply that it's effectively the same as a NOP instruction. Hex 90, which literally does nothing, and for those who don't know, NOP in assembly terms is actually an alias for the instruction exchange EAX. Now, in ROP land, a ROP knock is effectively an instruction in ROP that does nothing. The difference being it does actually execute a ret and shifts the stack pointer down. So what I'm going to do here is I'm going to change this EEE to a P32 of ROP knock address. Now, this I'm going to leave as FFF. I'm going to put a comment here saying this is ignored. And then I'm going to put just a few other ROP knocks at the end. And I'm going to show you why I'm leaving that in as we go. Alright, so bear with me while I quickly reset the state of this thing. kick off, skip all the breakpoints, try it, kick off the socks proxy. Okay, so for those who aren't familiar with ROP again, I'm hoping that this next little bit is going to help. So, to recap, we've smashed the stack, we've overwritten so much data that we've clobbered the SEH chain. The SEH chain now points to a stack pivot, which you can see here, that moves ESP down into our payload. And as you can see here, that the instruction that we've landed on is at 0455 DA0. That is a return instruction. Now watch this. This is important. The current instruction that we've got here is return 4, and again what that says is do a classic return, but then move ESP down further by however many bytes as specified in the instruction. So this will move 00455 DA0 into EIP, and then ESP will become F9C8. So this FFFF will just disappear. Okay, you ready? There we go. So this is where the glory of ROP kicks in. We now have the ability to control the stack pointer, and the stack pointer is now going to be abused to get EIP to go to various areas of code that we know is executable in memory already, and will be regardless of whether dep is enabled or not. So what we're seeing here is ESP, which we control, currently says, right, I want you to go to a return instruction. So if we look on the top left, that's where EIP currently points to. Now when we execute this, remember we're executing code in the context of the current application. This is in the code segment. See, 00455 DA0. That is in here. There you go. That is readable and executable. So we know that whatever bits of code are in that segment are going to be executable, right? So that's what that is. We're just executing a single return, but in the process, you should notice that ESP should drop down to CC, and then D0, and then D4, okay? So if we step into this, press once, there you go. We've actually gone back to the same instruction. What's happening is that we're popping a value from ESP into EIP, and ESP drops by 4, or I should say increases by 4 bytes, and then hence moves downwards. So every single time we execute that, we're effectively doing a NOP. We're just running return and jumping to the next return. Now, to demonstrate what I mean by ROP gadgets that actually paint some values in memory that we find interesting, what I'm going to do is I'm just going to open up ROP.txt. And let's see if there is a pop EAX ret. There we go. So here you can see here we've got one address that points to an area of memory that contains a pop EAX followed by a return. Okay. I'm just going to go to that area of memory here and make sure. It's very important at this point to highlight that as good as Mona is, if you're going to rely on a gadget, you should make sure that the gadget that Mona spits out is the gadget that you actually want. Okay, so we can see here pop EAX written. That's exactly what I'm looking for, and I'm going to do this purely because I want you to see how you can use small gadgets to manipulate the contents of registers. Okay, so let's take that address. Right, so this is where we're going to shove some gadgets here, right? Pop EAX ret. That's the address for a pop EAX ret. So what I'm going to do now is we're just going to ignore that and leave that as is. But after the first call, what I'm going to do instead is we're going to say pop EAX ret is the address that I want in my ROP chain. And then After that, I want to take the value of 1111 and I want that to go into EAX. Then I'm going to do it again. And we'll go 2222. And this time we'll go 3333. Alright, so the reason why I'm creating this chain is because hopefully through stepping through this, you guys will be able to see how the values of the register changes. And I'm not going to harp on this too much. This is just for those people who aren't quite clued in with how ROPs and how the chains actually go together and how you can manipulate registers as you go. Alright, so again, quickly spin up. If I could make this faster, I promise I would, but I can't, so I won't. Any questions from you guys while I'm spinning this up again? Am I failing at explaining? Alright, pivot, step, ret. Let's have a look. Still no questions? Alright, so we've gone past our pivot and we're effectively executing our ROP chain. So as you can see here, at the top of the stack, we have a pointer to another area of memory followed by 1111. Okay, so when I execute this return, you'll see that ESP moves down to where the 1111 is. So the first question you may have when looking at this chain is like, 1111 is clearly an invalid address. How is that going to work when ESP pops that into EIP? Well, this is where the chain comes in. This is where our gadget comes in. So you can see this instruction that we pointed it at says pop EAX. So what that's doing is it's going to take the value at the top of the stack and drop that into EAX while decrementing. So as you can see, this 1111 should change the value of EAX up here as soon as I hit go. There it is. So EAX now contains exactly what we want it to do. And then when we go retin, it comes back again. And now we want to pop 2222 in. Boom, there it is again, 2222. Right? And so we can continue to do that and manipulate the content of EAX just by using that very simple gadget. All right? Now that is like the fundamental building block of anything that you're going to do with ROP. The only reason why it gets more complex than this is because sometimes it's hard to get a particular value in a certain register, or the actual gadgets themselves are quite complex. But fundamentally, you're using just little bits of code from all over the application and gluing them together in such a way, using the stack pointer along with some other interleaved values that will allow you to take content that you control and start putting them in registers in a certain way. Okay, so let's assume that we're in a position to be able to change the contents of all of the registers, right? Why is that useful? Well, the main reason why this is useful is because what we want to be able to do is when we're ROPing, we need to be able to either allocate some memory that is executable, preferably read-write executable. We want to and then copy our payload to it, or we want to mark an existing area of memory as executable that already contains our code. So preferably it would be the latter, because that's substantially easier. Now there are a number of different ways that you can change the memory protection of a given page on Windows, and the two main functions that we tend to use to do that are called virtual protect and virtual alloc. I tend to gear towards virtual protect because virtual protect it just makes more sense to me. As an Xcoder to go, I want to change memory protection, so I'll go with virtual protect. But virtual alloc actually works in exactly the same way as virtual protect when you set a certain parameter to the same thing. So anyway, this is all well and good, right? We know that we want to be able to protect or change the protection of memory. So let's just have a look at virtual alloc. and virtual protect. Virtual alloc, virtual protect. Alright, so virtual protect, you can see here, it takes 4 values. It says, give me the address that you want to change, tell me how many bytes you want to change, and tell me what protection flags you want the memory to be marked as, and I'll return, should it be successful, the value of what the previous memory protection was. Okay, so this is a 4-parameter function. Now, just a quick note, the address here that we pass into virtual protect doesn't have to be the same as what you would expect to see when you were doing this on Linux. So on Linux, you have to make sure the address you give it is aligned to a memory page, otherwise it'll crash. Thankfully, in Windows land, we don't have to care about that at all. Size, it specifies the number of bytes, but again, it doesn't actually have to be the page size itself. It can basically be 1, so that certainly makes it a little bit easier. Let's have a look. We've got some questions. Grand Vizier P, you are very clear on what you did. You made my day. Oh, awesome, dude. That's really good to hear. I really hope that sort of made things gel a little nicer for you. Just in case I stream, how many hours of work arrive at this stage? Yeah, we're in about 2 hours, as the guys have already said. So I've been a little bit verbose and I've been flapping about a little bit and failing, but you know, hopefully people are learning from it as we go. So virtual protect is one function. Virtual alloc, as you can see, it's exactly the same signature as far as count of arguments is concerned. The main difference being that you have to specify an allocation type rather than a buffer that receives the protection type. And this comes with the quirk that if you specify the same address that's already been allocated, you are effectively just changing the memory protections on an already allocated area of memory. But as I said, I tend to gear towards virtual protect. So, regardless of which function we choose, how do we call it? Okay, we need to be able to call the function virtual protect in 32-bit land. Ha, I'm OPSEC failing again. Ignore my signal notifications. Lockefer, this has been fantastic. I'm off to bed. We'll watch the archive later. Cheers, Lockefer. Thanks a lot for coming along, man. Really appreciate the feedback. Right, so where were we at? Right, so we have a function that we want to call, but in 32-bit land, we need to pass these parameters on the stack. So we need to be able to take some values that we control and somehow get them on the stack. We need to create what is effectively a fake stack frame that says, I want you to invoke virtual protect with these 4 parameters. And that means we need to know what the stack layout looks like at the time of calling. We need to know what those parameters needs to be. We need to somehow get those parameters onto the stack on the fly. And that's kind of where the trick comes in. So what we need to be able to do, in order to be able to achieve this, there's 2 sort of main ways that you can use ROP to construct values or write values to the stack. The first and probably less common one is using something called a writer gadget. And a writer gadget is something that may take the content of a register and write it to some memory location that you can control. When you do that, after a series of attempts, you effectively are just painting values to the stack as you go, and then what you need to do is pivot the stack back to the fake stack frame to invoke your function call. That's not my preferred method. The method that I tend to prefer, and what I've seen other people prefer, is making use of something called a pushAD ret. So pushAD is an assembly instruction. Let's see if this is a useful bit of documentation. So pushAD says push EAX ECX EAX, ECX, EDX, EBX, original ESP, EBP, ESI, and EDI to the stack. Right, so what that means is every register that we have gets written to the stack, which is pretty cool, right? Because that effectively takes all of the registers, which we can manipulate with our ROP gadgets, takes all of those values and paints it to the stack in one foul swoop. So that gives us our the thing that we need. ESP is then at the start of that area that we've painted because it's written them all to the stack. So what we need to be able to do is return immediately. And so when we return, the top value that we've specified is then used as a return address. And so we can use that to pass control to virtual protect in order to execute our function. So we can like paint our arguments, right? Paint our arguments, followed by the address of the function that we want to invoke, and off we go. Now that's all well and good. Once that's been executed though, we need to make sure that control is returned to us and that we don't die. Now in our case, what we're going to do is this. We're going to attempt to call virtual protect. We're going to pass in the address of the stack because we want to mark the stack as executable, right? We're going to put in some other constants. We're going to say, you know, we want to make sure that the memory is read-write executable. We're going to have some value that's writable somewhere in memory because we need to pass a pointer to virtual protect, as you can see here, for old protect. So we just need a writable area of memory. We don't really care exactly where that is. And we need to pass a non-zero size to say, can you please mark this page as executable? Then when that's done, when it returns, we literally want to return to an instruction that allows us to jump to the area of memory immediately following our ROP chain so that it executes, right? But we'll get to that later. So first thing we need to do is we need to say, how are we going to be able to construct in memory a series of ROP gadgets that will allow us to call virtual protect with the data that we actually need? Well, this is where Mona comes in. So as I said, when we call bang Mona ROP, what we can do is say, go and check out all the areas of memory that we're interested in and find out a series of ROP gadgets that are useful to us. At the same time, it will generate something called ROP suggestions, and this is fabulous. Do not underestimate just how fabulous this is, because it really is truly fabulous. As you can see, sorry, not ROP suggestions, ROP chains. You can see here, it'll generate this file and it says, this is the register setup that you need for virtual protect. And here is a sample ROP chain. We'll scroll down to the Python version. Here's a sample ROP chain that actually calls virtual protect. So here you can see pop EVP, pop EVX, you can see here, pop EVX written. Here it's actually doing some magic to set EDX to 0, and then you can see it's writing a value from EVX to EDX. So this chain here is slowly but surely actually grabbing all the bits and pieces that it needs and painting the data to memory, to the registers for us. So this is nothing short of brilliant. What you will notice, I should say, is that while it does a fantastic job of giving you the bulk of what you need, it's not perfect. So, standard approach. Oops. I'm going to paste the ROP chain in here, and now I'm probably going to get rid of this window down the bottom, given that we don't really need it. Let's space this out a little bit so people can see. If you can't see that, let me know, but I'm pretty sure it'll be okay. Right, so this is the ROP chain. Now, one thing to note here, see how this says, this line here, pointed to the address of virtual protect. Skipped module criteria, check if pointer is reliable. So what this is trying to do is we need to be able to specify a pointer to the virtual protect function so that the ROP chain, when it runs, actually does exactly what we would expect. The problem we've got here is that this address, which is a pointer that points to virtual protect, is that it's probably in an area of memory that is ASLR'd. And we can validate that by checking out the VM memory map right now. So according to that address, which one? Sorry, what was it again? It was 77A0114. 77A. It's not even in there. So, needless to say, I mean, this is saying that it's actually part of OLE32 com dialog secos, whereas the gadget that I generated earlier was from kernel 32. Oh, hang on, have I got it wrong again? 770A, okay, it does, 770. So it's in here. Sorry, in here? In here. So what it's doing is that it's using the import table. But the problem we've got is that every time we run the application, kernel 32 is going to be in a different location. And so we can't rely on that address being correct every time that we run it, right? So that's something that we're going to have to fix. And we can do that using a number of different methods. But to begin with, what I'm going to do is I'm just going to demonstrate what this ROP chain does. Okay, so that generates the chain. What I'm going to do is get rid of all of these ROP nops. Where are we? I need those. Okay, so from here I'm going to do create ROP chain. So create ROP chain obviously calls this thing here, and we should be able to see each one of these, assuming there's no bad characters. Okay, and what I'm going to do is I'm going to step through this just to show you what it currently does, and from there kind of show you how the whole process of getting all the arguments mapped correctly to the registers, followed by pushing and retting, actually behaves. Bed for me too, approaching 1 AM. Yeah, for sure. Thanks a lot, Jadeth. You take it easy, man. Thanks for coming. All right. So with that out of the way, let's clear this up just a little bit. I'm going to continue to leave this in here because I want the payload size to be the same size. Let's kick this off. Rinse, repeat again. I feel shells coming. They're on their way. Okay. Alright, back to exploit land, run it. Back to the VM, stack pivot, boom. Okay, here we go. So I'm just skipping over what we had before, and this is what looks to be a few ROP nops. Right, let's just make sure that's correct. Woo. So we've got, where are we? ROP nop address is DA0. Yep, okay, so that was right. Okay, so we had our first ROP nop just there. So next instruction, it says, let's just ret, and ESP should drop down by 1. Now here it's popping a value into ESP, and it's actually popping the value that is the address of the instruction that's currently being run. Okay, now why is that? Let's just have a look back over here where these ROP chains are. You'll see what it says here is that calling virtual protect, EBX needs to be a size, DW size, right? Which doesn't really make a great deal of sense. That this particular ROP chain is dropping an arbitrary value into, hang on, it's EBP. What am I talking about? EBP. Ah, it's a return to pointer. So this should be a jump to ESP apparently. it again. I don't think that that's what's going to happen. Let's skip over this for now. So we've got EBP, as you can see, now points to the instruction of pop EBP, right? But we may find that the return of this will contain a pointer to ESP after the fact. All right, so I call ret. Now the next thing we're doing is we're popping the value of 201 hex into EBX. Again, if we go back to ROP chains, we can see EBX is the size. Now, 201 for some reason tends to be used all over the shop when Mona generates these ROP chains, but technically the size could be really, really small. As long as it's non-zero, it will still modify the entire page. If you did want multiple pages to be marked as executable, then you would have to make sure that the size is bigger than one whole page size, and that would guarantee that you would get 2 pages worth should we currently be page aligned. Okay, so EBX now contains 201. All right, so next up, EBX. We're popping the value of 40 into EBX. So you'll see EBX, oh geez, have I got it wrong again? I have got it wrong again. So we've got EBX, which was 201 and now is 240. Now I think what we're seeing here is we've got a slight ordering problem. Like there are values that we want in EBX, but now we're actually going to abuse EBX to get a value in a different register. So 40 is looking to be the size. And then the next thing we do is we're clearing out EDX and setting EDX to 0. You can see that there. And then we're using a different gadget to add the value of EBX to EDX. Right? You can see that there. So that is a way of getting a value into the EDX register. Let's clarify that a little bit by looking at this. All right, so let's put some gaps in here. Right, so let's just make sure that we know what we're doing. Now, as we can see here, we were just basically pulling a value into EBP that we didn't really care about. So let's ignore that for now. EBX needs to be set to 201 because that's the size. However, this next thing here, we pop EBX again, clear EDX, and then add the value from EBX into EDX. So that takes the value of EBX and puts it into EDX. But in the process, we're clearly killing EBX. So what we need to do is, all right, so that's part of the same gadget. We need to move this down here. So we'll call set EBX there, and we'll call EDX there. And what I might do is put a smashes EBX comment in there, because that will allow us, like later on when we're reading, to know, oh, we've got to make sure that EBX is set after we've set EDX, purely because this is clobbering the value of the register as we go. Okay, so we've got 16 bytes that we need to worry about. Okay, so we've added EBX, that's going to go into EBX, and then we're going to return 10. So that means we need to take these fillers out and put them where? There. Okay, because that will compensate for this return 10 here. So this hex 10 says, remember, we are going to, once we've popped a value from the top of the stack into EIP, we're going to move ESP back down because of the standard call calling convention. So when we add EDX to EBX, that will take the value of 40 and put that into EDX. Then it pops a value into EBX. That's what this filler here is, right? So, and then it does this return 10. Now, what's interesting about this, as you can see, is the next thing we do is we go pop EBX written. Well, you know what? We don't need to do that as two separate instructions. We can actually set EDX and EBX in one fell swoop by taking that and replacing it there. So this is going to make our ROP chain just a little bit shorter, right? So we can pop EBX at the same time and set 201, and then we don't actually need to worry about setting EBX separately. Okay? Now we do need to worry about these fillers still, right? So once this is executed, and we call retin10, this is the next thing that's going to be executed, is this pop ECX. So that means the fillers need to go immediately after. Right, so here we're setting ECX. We should probably put a comment here to say that we're setting EDP. Right, so that's EDX set. Set EDI by the looks of it. Doesn't look like it's doing anything too nefarious. Set ESI, same story there. You can see it's not doing anything particularly special. This is doing EAX. Yep, again, that's just a pop ret, pop ret, pop ret. So none of these instructions here, that pop ret, none of those are actually munging any other registers. And finally, call virtual. I should probably be more accurate and go virtual protect. Now, the main concern that we've got at this point is this. Okay, this value, this particular gadget here is bound very much to kernel 32 as it currently stands. So we're going to need to do some smarts after this, but for the sake of this little demonstration, I think we'll go ahead and actually see this in action. Okay, so let's quickly back to the VM. Spin our application up again. Have I lost everyone, or are you all still with me? We're getting close now. We're getting really close. Everyone's very quiet. Okay. So again, remember this is what we're looking for. One of these two. Okay. I'm guessing that this second one is the way that we're going ahead. Anyway, so bear this in mind. This is what we're aiming for. Okay. Go. Righto, we've got our exception. Stack pivot. And bang, here we go. Okay, so we're doing what we did with EBP. We're just setting it to an arbitrary value. Now, why are we popping EBX again? Did I not save it? That shouldn't be the next thing we do, should it? Pop EBX written. Yes, that's exactly what we should be doing. That's a relief. So we need to pop EBX, and we've got the value of 40 now in EBX. Next thing we'll be doing is clearing out EDX with an XOR, sorry, followed by adding EBX to EDX. So that means EDX should become 40. Yep, perfect. Thanks, Pritchas. Appreciate that, mate. Then we pop EBX. Here we go. So we can see EBX is now 201. That was the little tweak that we made. So we don't need a separate pop EBX again, because we can abuse the tail end of the gadget that we're using here, this pop EBX, to actually put the value in EBX at the same time as setting EDX. Followed by retin10. So when we call this, this is where we'll go, and then these 16 bytes will be skipped. We should see F8 being at the top of the stack. Okay, so let's step in. Boom. Sounding like Steve Jobs. Boom. We are now here. We've got pop ECX is the next one. So pop ECX points to this area of memory here. Now ECX needs to contain a pointer to a writable area of memory. So this is probably in BSS or something like that. But as long as it's read-write, it's fine, because that's where the existing memory protection value is going to be set. Okay. And then we return. Next, we're popping EDI. EDI, what does EDI need to be? I forgot about that. EDI, a ROP-NOP. Okay, so a ROP-NOP, and the reason why is it's a ROP-NOP, it needs to be a ROP-NOP. I will explain when we get to the point when we're actually about to call virtual protect. This whole thing is amazing, best thing ever. Thanks, dude, that's awesome feedback. Okay, so let's step over the popping of EDI and return. Same story with ESI. We're just going to drop a value straight into ESI. That needs to be, in this case, it's going to be a pointer to jump EAX, because EAX is actually going to point to virtual protect, right? So see that? Pointer to virtual protect, and ESI needs to be a pointer to jump EAX. So if we pop ESI, and then we basically say, where are we? Follow in disassembler, you can see it's jump D word EAX. So that is doing exactly what we would expect. All right. So next, we're popping the value of virtual protect into EAX, or I should say a pointer to. So if you follow this in the dump, you'll see that that contains a pointer to 76CA2CF0, right? And that should be pointing to virtual protect. Okay? Right, here's where the magic actually happens. So if we have a look at, we've got EAX, ECX, EDX, EBX all set to what we want. EVP, ESI, EDI, again, all set to what we want. When we call push AD, you should see this, all those values get written to the stack. Okay? There we go. So now push AD has taken all of the values of the registers that we want and actually painted the stack with the arguments. Now let's confirm this, right? Let's just quickly look at the documentation again for virtual protect. So size is the second parameter, and we know that size is going to be 40. So that means the first parameter is this, right? So the second parameter is, sorry, is that right? Size, I can't remember which one's which. It's in reverse order. So this is size, that's the new memory protections, and that's a writable area of memory. So this here is the value that we're changing, okay? And you'll notice this value, FA18, points directly to where we are currently on the stack. So we're going to be marking the current page. Yes, thanks Justin, you're right mate, that 201 is the size. So 201 is the size, 40 is the memory protection value that we are changing. This value here is a writable area of memory that'll receive the old virtual protect, and this is a pointer to the area of memory that we want to have marked as executable. So this means that we are about to finish executing this gadget. Now what's important to note here is after we've done a push AD, the very first, the stuff I think that's at the top of the stack is EDI. Is it EDI? Yeah, so EDI contains a ROP-NOP because all the other bits are out of whack by 1, and so what we need to do is just basically move down by 1 so that everything else lines up. We're effectively skipping EDI by doing this, okay? So when we call return, we get a ROP-NOP, okay? And then at this point, we call jump dword EAX. So EAX, as you can see, points to the virtual protect constant. And when we step in here, hopefully, here we go, you see this? We've now got a call to virtual protect. The address is wrong, the size is wrong, new protection is wrong, and the old protect is wrong. You know why this is the case? It's because we've got our function call shifted by 1. All right, so we're calling virtual protect EX, and by the looks of it, maybe, see how it's got virtual protect EX rather than virtual protect. So what Mona has generated for us in rotchains. Where are we? Python. Here we go. So it's saying here, pointer to virtual protect, right? So the problem that we've got here is that virtual protect and virtual protect EX are not the same things. By the looks of it, it's possibly confused one with the other. So you see virtual protect EX takes another parameter, right? And that is the handle of the current process. Everything else is exactly the same. So that's what's causing our function to be off, our function call to be off by 1. So instead of virtual protect EX, what we're looking for is actually virtual protect. So what we need to do is we need to look at the import address table and find out exactly where virtual protect is rather than the virtual protect EX. And I can't remember how I did that. So, but what I do know is that it's going to be in kernel 32, wherever that is. Could even be in kernel base. Kernel 32. So kernel 32 is, yeah, that's exactly where, I think that's where virtual protect is going to be living. So now we need to figure out exactly where virtual protect is rather than virtual protect EX. Another option is to change it so that we specify a valid process handle. But I think going down that path at this particular point will be a little bit unnecessary. Just quickly while I remember, given that we're getting very, very close to nailing this, what I'm going to do is change this last part so that we have a bunch of breakpoints instead of just arbitrary random ASCII characters. So that means that when we're done and everything works correctly, we'll just hit a breakpoint of our own. And then from there, we know that we could add our own payload, which we'll do, and we'll get shells by the end because everybody loves shells. So let's just quickly go back to here. So what we need to do is we need to find where virtual protect is. That's not what I'm looking for. Now I would do this in what's it called? Differently in WinDBG. So what I'm looking for is, how do we go about finding the address of virtual protect? I want to find imports. Can we find imports in here easily? Handles, threads, memory, executable modules, source files, etc. Where are we? Patches, handles, windows, threads, memory. What do we got here? Nope, that's not what I'm looking for. Alright, let's noob it up. Anyone know how to find, I can't remember this off the top of my head. What's this? Teach me how to hack an email. Ha! I'll let Justin handle that question. Immune debugger, find function. Find address from function name. Search for. Here we go. There we go. Name in all modules. address module name. Okay, so wow, that's ugly as sin, isn't it? Can we find in here? So by search for all readable, including anything we go to search for name and all modules, current module. Well, that's certainly handy, but the names are terribly bad. So what we would need to do is maybe we can order this by address instead. NTDLL, SVC, WS32, com dialog, com base, kernel 32. Okay, so based on the name we saw here, API MS Win Core Memory, let's go down this way. Localization, memory, virtual protect, there it is. So we're off by 4 bytes, check that out. So we've got 114 and we need 118. There you go, I just learned something. Thanks, Justin. Absolutely spot on. There'll be no illegal shenanigans going on around here, so please don't even ask. Right, so let's change that virtual protect to 8. See, this is, as much as we love Mona, sometimes it can be just slightly off. Maybe it did a substring match. Hey, that could be a bug. Check it out. It found virtual protect before it and didn't necessarily cater for the EX. So that's cool. All right, let's run this shizen again. Back to the CPU window. Everyone still playing along? Haven't lost too many more folks, which is cool. Righto, I'm feeling good about this. Alrighty, here we go. Let's make sure we've saved. Go. Run, pivot, ret. Okay, so I'm just going to step through this again really quickly. We get to the point where, there you go, check that out. So EAX now actually points to virtual protect this time. Push AD ret. Boom. Step in. Okay, that's better. Check it out. Okay, so we're calling virtual protect. The address is pointing to the stack down here. Size is 201. And new protect says page execute read write, which is awesome. Alt protect is just a pointer somewhere. So what I'm going to do is I'm going to step over. It's F8, isn't it? So I'm just going to keep doing this and stepping over, because what I want to see when it's done. Right. So at this point, the function has actually finished executing. So let's just quickly check to see if the stack is now marked as read write executable. Where was it? It was this one here, wasn't it? Doesn't look good. So EAX returned 1. Now, according to the documentation for virtual protect, returns a Boolean. If the function succeeds, the return value is non-zero. If the function fails, the return value is 0. So according to this, with EAX coming back as that should be exactly fine. Well, let's see what happens at this point. So when we return, pop EBP return says push EBP return. And look at that. Check that out, just like a bought one. We can debug, we can step over our instructions. There you go, we're actually technically currently running our payload. So what's happened is the virtual protect call succeeded. We've popped back out. According to all of the things, this should technically work. This should all just behave itself. We managed to construct a correct call to hey Dimitri, yeah, you're welcome, dude. Thanks a lot for coming along. So yeah, what we've done is we've constructed all of the parameters correctly in memory, inside the registers. We've used a push AD instruction to paint all of the content of the registers to the stack. We've then executed a ret, which immediately begins with a ROP knot to move ESP down. We then have a fake stack frame set up so that virtual protect is called. Virtual protect marks the stack, hopefully, as read-write executable and returns. We then pop over the top of the tail end of our fake stack frame well into our area of shellcode. And our shellcode at that point should be marked as executable, and off we go. Now let's just see how many bytes. We've got quite a few bytes. Quite a few bytes sitting here. So what I'm going to do is I'm going to look for a different instruction for this. Is it this line here? There was a pop, a push ESP ret, which we added to our chain. So this is the last thing here, pointer to a push ESP ret. So I'd like to find another one of those that doesn't do the, that doesn't use standard calling conventions. So what I'm going to do is quickly go into ROP. Pardon me. I'm looking for a push ESP ret that doesn't have, let's have a look. That might actually be the smallest one we've got, 0C, 1C, 18. Yeah, so 0C, we're going to have to skip 12 bytes whether we like it or not, which is a bit of a shame. But that's okay, it could be a lot worse. Okay, so because I don't believe in NOP sleds as far as the exploit is concerned, Matrix Kid 44. What do I have to learn to start understanding the things you're saying? Maybe if this stuff is new to you, Matrix, the best thing I think that you could do is take a look at Justin Stevens' Do Stack Buffer Overflow Good tutorial, and begin with that before you start tackling what I'm looking at here. So Justin, would you mind sharing the link to your Do Stack Buffer Overflow Good for those people who are new to this stuff? Because we're talking about some things that are a little bit more advanced, and if this is kind of unfamiliar, I'd recommend Justin's tutorial as a really good starting point. There's a fantastic PDF, a really good set of tutorials. There's even a talk out there on the internet about it, and there's a bunch of people who have gone through it themselves. And Justin, who, as you can see, is saying, ooh, a plug, he's pretty much on call to help anybody else who wants to learn. So big thumbs up from me on Do Stack Buffer Overflow Good as a starting point. So, all right, so what I'm going to do is I'm just going to quickly rerun this to a point where I can figure out exactly where I need to be memory-wise. Because as I said, I don't like NOP sleds, they make me sad. I like to very much be exact when I'm doing my exploitation. So let's just quickly run this again. Go back to our ROP chain, spin it up, let it run. Okay, push 80, push AL, retin. Skip over the top of the virtual protect call. Pop EV retin 10. Pop EVP. Retin. Okay, so this has gone to 1C. We don't really want the 1C, so let's use a different gadget for that, because I think 0C is going to be enough. So let's take this one. We'll go to that address, and we'll use this one instead. Copy to clipboard. Let's go back to our exploit. Pointer to push EBP ret 0C. What did I do? Yeah, I did that right. So that means we're not going to be moving quite so far. Let's take a copy of that address, and I'm going to cheat and drop that into, where are we? Can I modify this? That's right, I'm going to set new origin here. Here we go. So that'll go push ESP retin 0C. Okay. So that means, right, so we are basically at the point that we need to be at immediately afterwards, but ESP has been moved down here. Now, trap for young players. The start of our shellcode is actually above ESP. That's really bad. So ESP is currently set to A28 and EIP is set to 1C. So that means we are, what, 12 bytes off. Right? So what we actually want to be able to do is move ESP up a little bit, because we don't want any shenanigans to do with our payload to cause anything to go wrong. So I'm going to add a whole 16 bytes to ESP, because that will, subtract from ESP 16 bytes, because that will move ESP to something higher than EIP. So as EIP is executing, nothing that happens with the stack pointer should hopefully cause any pain. To do that, let's go to our beloved Metasploit framework. Don't do that to me. Tools, exploit, Metasm shell. Man, can you believe it? This is what happens when you update Metasploit framework. Vim Ruby version. Shouldn't have to do this. Exploit Metasm shell. There we go. Just give me a sec to, unfortunately, bundle install because reasons. Yeah, so what happened was earlier today I updated Metasploit, and behind the scenes clearly it did some shenanigans on Ruby versions and whatnot. And right now I would assume that Justin's frantically vomiting in his mouth because I'm using RVM. This is embarrassing to be showing on stream, isn't it, hey? God, man. You gotta be kidding me. Alright, bugger that because reasons. Instead, we'll do it the old-fashioned way. Exactly how that will be done, I'm not exactly sure. Actually, maybe I can do it this way. Code, Metasploit framework, tools, exploit. Will that work? Really? Just give me a sec to do some off-screen stuff. Just when you thought this won't take long. Sorry about this. This will teach me to update prior to doing a stream. Okay, here we go. So what we want to be able to do is sub ESP 16 bytes hex. There we go. There's our byte sequence. All right, so the start of our payload, we're going to go hex 83, hex EC, hex 10. And let's put a little comment in there. There you go. So that should move ESP, and then we know that whatever payload it is we decide to generate after the fact is going to be fine. My concern now is that I'm probably not. Oh no, I can cheat somehow. Yeah, that's what I'm going to do. Because I want to shell this. I actually want shells to come out at the end. We're so close, it'd be such a shame to not shell this thing. So let's just add some NOPs so that we can see things running, and then we'll add a few breakpoints. Okay, so I'm not condoning the use of NOPs and breakpoints, by the way. I just want to see this running. We may still need to fix up our import address table hopping, because it looks like we're using a hard-coded address that we can't necessarily rely on. We'll validate that shortly, but we're pretty close at least. All right, pivot to our construction of our virtual protect call. Push, ret, jump, actually do the memory protection call, step in, copy DP, ret, push EAP, ret. Okay, so ESP currently points to 28 and EIP is 1C. There you go. Now we're in completely different areas, which is fabulous. So now our NOPs can run and we hit our breakpoint. So we do now have a case where we can actually generate a payload, which is great. Justin, to answer your question, yes, MSF did bump recently, as in very, very recently, and I didn't want to go through the pain of having RVM run and install sort of behind the scenes without you guys watching. So what I'm going to do instead is, what am I going to do instead? I may actually have to, which would be crap. Anyway, so what I can tell, we've actually got code execution. What I think we should do, I need to generate a payload. What I think I'm going to do is just use netcat, and I'll generate a payload on a different machine, which is slightly off screen. I apologize for this, but clearly my Metasploit install is not behaving. So what I'm going to do, I'm just going to kick this off now. Excuse me just a minute. I may even try, actually no, it's probably worth, is 2.3.1 the latest one? Yeah, no. Yeah, that should be fine. So Ah, it's working. Excellent. Okay, so MSF Venom. So we're going to do a... Should we just do a plain old shell? Windows... what am I looking for? Windows shell. Let's just do a shell reverse TCP. Output, we'll go 8000. Format raw. Output to stream revshell.bin. Am I doing anything silly there? Windows reverse TCP. No. Here we can just add revshell.bin. Okay, it's sitting there, so let's just go nclvp 8000. Now let's just make sure this is running again. You guys ready to do the shell dance? Yeah, Justin, that's exactly what I was doing before, but for some reason it wasn't working with the Metasm shell stuff. But it clearly seems to be working with MSF console directly, so okay, so it's running. Hopefully we should be able to just let this run. Boom! Fuck yeah, happy with that. All right, let's do it with Meterpreter. Doesn't really seem to be any bad characters at all, does there? Actually, MSFM, let's call that revnet. We'll keep everything else the same. There it is, revnet, revshell, MSF console -qx. Use multi-handler. Set payload, Windows, interpreter, reverse TCP, set lhost, oops. 1.10.40, set lport 8000, set exit on session false, run /j. That's exciting. I love shells. So, whoa, what's going on there? That looks buggy as hell, doesn't it? All right, at least we've got a job running. Now, what I'm going to do this time, actually, I will run it within the debugger once, and then I'm going to run it outside of the debugger. And if it runs outside of the debugger, it's probably fair to say that that address that we're relying on is not being subject to ASLR, which would be great. However, I get the feeling that it will be. All right, here we go. Let's see some interpreter magic. Oh man, check this out. You know what's going on? So as a Meterpreter developer, I have been known to build DLLs myself. And so if you have DLLs in your data Meterpreter folder that are out of sync with your framework, which is clearly what's just happened, then things get very upset. Let's restart this again. Pro tip, make sure you clear out your data Meterpreter folder of any stray DLLs before you stream. I'm going to be adding that shit very shortly. Would have the right to click. I was waiting for you to start the get system jokes, Justin. Okay, here we go. Man, what a mess. Okay. Go. Make it so. Make it happen. Oops. Get UID. Alright. Sweet. It works. We got shells. Okay, so I'm going to exit that. And now I'm going to run it outside of the debugger. Okay, so let's just let it run. Now my feeling is that it's not going to work outside the debugger. That's just gut feeling. Let's find out. Oh, 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 it works. Oh. Sweet. Check that out. Okay, so it does work. It looks like it was correctly resolving based on a non-ASLR'd IAT entry. So how exciting is that? That's pretty cool. So there you go. We're done. We got shells, repeatable shells using ROP. And yeah, I hope you guys and gals out there enjoyed and learned stuff. Now, bear in mind, I'm just going to highlight this line here before our payload. If you don't do this and you use payload encoding, then seriously, you will end up in pain. Switch, answer my question. What is your question? Juice, can you explain what platform Windows actually does when generating a payload? Yes, I can tell you that. When you specify the platform on the command line in Venom, you're forcing it to choose a platform that isn't specific to the payload. So for example, there are, maybe I can show you this. So, you can see in here there are quite a few payloads in Metasploit, right? Some of them have platforms, some of them don't. So if we go up to, where are we? Generic shell bind TCP, for example. So if you tried to create something with this, it wouldn't really know what platform to use. So you could go generic shell bind TCP platform Windows, and that will tell it to use the Windows platform instead. If you use one of these payloads where the platform is actually specific, then you don't actually need to, because if we do Venom, where are we? Let's just run this again. So you see this here, no platform was selected, choosing that from the payload. Okay, so if you have a payload that doesn't have a platform baked into it, which is what the generic ones have, then it won't work, and you need to specify -- platform on the command line. However, you don't need to do that. If you specify an actual specific payload, so you know, if we did a 64-bit version, pardon me, again, it's able to pull Arch x64. You see this one here was x86. It's been able to pull x64 out of the payload there. So Arch and payload don't need to be specified unless you're using something that's generic. At that point, MSF will complain. But for the most part, if you're using platform-specific payloads, then you don't need to specify platform at all. Cool. Does that answer your question, Switch? Awesome. Does anyone else have any other questions? Are there things that you want me to hit before closing out? 3 hours. That's actually not too bad. I was expecting it to be a little bit worse. Comments, feedback, questions, etc. welcome now or later. You can abuse me publicly if you prefer. I have no problem with that, but you know, hopefully... Ha! I'm failing at OPSEC again. Where did you learn these things? Oh, you know what I should do is go signal. How reliable is the distance you calculated for the stack pivot caused by the exception throwing? I would say that's pretty reliable. I don't have any stats on that, to be honest, but there's always the potential for platform-specific differences. I mean, I haven't run this on Windows 8. Obviously, I haven't run it on Windows 7. I don't know what differences we're going to end up seeing. Maybe I can play with that on a different stream or whatever. But yeah, exactly. I mean, that's the thing, that there's a good chance that your ROP chain will need to change depending on the OS that you're running. But again, for the most part, it should be relatively sane. But again, I can't say for sure. I have noticed differences, particularly when it comes to exception handling between Windows 7 and Windows 10, but they haven't necessarily been huge. But I would say that you would probably see some nuanced differences between the two. The sprinkler is on because it's been hot during the day, and on my side of the planet, if you leave the sprinkler on during the day, then the water just literally evaporates. And if you do it during the night, like now, the water has a chance to soak into the grass before it evaporates. So there you go. You're not only learning something about exploitation via ROP, you know how to actually properly water your lawn in Australia. You're welcome. L. Pritchos, if Virtual Protect was subject to ASLR. So Virtual Protect itself is definitely subject to ASLR and will remain so. What's going on in this particular case, though, is that we're not referencing Virtual Protect directly. What we're doing is we're referring to the import address table inside the local image. So the application that's running has a reference that contains an import address. The import address is the address of where Virtual Protect lives in a separate binary. So instead of saying, hey, we're going to hard code the address of Virtual Protect, what we're doing is we're hard coding the import address of Virtual Protect, which doesn't change. So we can reference that to get the pointer to Virtual Protect rather than directly having a pointer to Virtual Protect itself. Does that help? Does that answer your question, Pritch? I'm hoping that's so. Hey, Smittix is here. How you going, dude? Yeah, you did miss it, but I'll archive this stuff on YouTube, as I always do. So I'll certainly be putting this up on YouTube for other people to laugh at. And I may just add hashtag sprinkler so that people know how to water their lawns properly. Tristan34, where did you learn these things and for what reason? So the reason why I learned it is because I find it interesting. I like the idea of figuring out how things work, what the nuances of various OSs are, and getting systems to behave in ways that they weren't really originally intended to behave. You know, that's effectively what hacking is, right? It's understand things at a much better level and see what you can do with it, you know? That was my motivation for learning this stuff, and that has been the case for quite some time. You better understand things, you're better able to protect them, protect yourself against them, you're better able to teach other people how these things work. And yeah, I think it's a good thing to sort of have that desire to just constantly prod and poke and improve. And and learn how things work. As far as how I got to the point where I understood what I understand, well, it kind of started during university days when I discovered Numega Soft Ice, and I spent a great deal of time playing around with that stuff, and the rest, as they say, is history. So yeah, I'd say that, followed by a pretty deep-seated interest in development, which I did for the first sort of 13, 14 years of my career. From there, I mean, I've worked in some pretty interesting environments, including like fighter jets. I've had code running on fighter jets. I've worked on console games. I've worked on voice over IP and encryption and all kinds of low-level stuff. So that sort of long-term exposure to low-level code has sort of kept me interested in the binary side, at least. So in particular, just playing around with things on the side and spending a lot of time building things and pulling things apart is effectively how I learned. Geez, I'm starting to get a good slew of questions now. Reskin, no, Tech Organic, that looks like Tech Organic is a Super Koji Man's blog, so I would assume that I have read that in the past, but that was quite a long time ago, and based on the link that you've put up there, 2014, that's also quite old. Game Me, how did I learn programming? Well, I was fortunate enough to be in a family that could afford a computer when I was a young kid. So at 7 years old, I was given a Commodore VIC-20, and from there I started playing with BASIC. As I leveled up through the years, I went from BASIC to C to C++, QBasic, and played around with a lot of crazy bits and pieces prior to even getting to university. And again, I was lucky enough to go to university, where I really started learning some interesting things, including the joys of functional programming, which I won't get on a soapbox about now because I could talk all night. But I've had an exposure to a lot of different languages over a long period of time, and then from there, moving from early days of university to a full, properly paid software engineering gig, and the rest, as they say, is history. Hacking isn't always getting into other computers or stealing info. That's exactly right, Wozniak. I completely agree with what you've just said. It's all about pulling things apart and just understanding how they work. The term hacker seems to have been associated with a very sort of negative connotation for the most part, and I don't really like to use that word anymore for that reason. But ultimately, it's just getting a better understanding and, you know, seeing how you can make things behave in ways they weren't originally intended to behave. Dover Yawn, do you do a hack every time you stream here? What will you do next? Yes, so this channel, this stream is dedicated specifically to various forms of security related streams and topics and tutorials. So far for me, it's been fairly heavily focused on binary exploitation. It's the thing that I do really enjoy. But that doesn't mean to say I'll be sticking to binary exploitation. There's a chance that I'll move into, you know, web-based CTFs or something similar. What will I do next? I don't know. I aim to stream once every 2 weeks, and I'm open to suggestions. It depends on what I'm interested in, what other people are interested in. If there's a particular thing people are interested in learning about, then I'm happy to do a stream on that. I like doing the kind of thing that I've done tonight because it includes me failing a lot. I think people seem to have a skewed view of how people do this. They have this pure path from A to B and they own things in 15 minutes. And yeah, that's generally not the case. So for the most part, I think it's really good to see if I have people see me flap about and make mistakes and see the thought process that I'm going through and understand that it's okay to take a long time and fail at stuff even though you've done this kind of thing before. So if you've got suggestions, you want me to focus on anything in particular, then, you know, let me know. Otherwise, I might pick a random challenge, I might pick a CTF, or I might even do some kind of, I don't know, maybe I'll do a development stream one day and show how you can hack some Metasploit or Meterpreter stuff together. Who knows? Pritchard missed something in the ROP chain. The point of the address virtual protect was not reliable as may be subject. However, in this case, it was not. That's exactly right. So in this case, the pointer to virtual protect was not ASLR'd, but virtual protect itself is ASLR'd. Thanks, Justin. Justin did in fact answer that question for me. Wozniak, like yesterday I watched a stream where they hacked an RC car and made it possible for viewers on Twitch to... That's cool. I'd like to have steered a car through the Twitch chat. That would have been pretty wicked. Time to get your hands on an IoT device and rip it to shreds. Hey, you know, that's a good idea. I've actually got some pretty crappy gadgets around here, so maybe what we can do is do another stream where just scan fuzz and try and own something like that and get some exploits going. What I might even do is make a point of getting PRs together for Metasploit modules and whatnot, so other people can learn from them after the fact. Okay, so that's pretty much the end of the questions. So given that oh no, we've got another one. Game me. How do you embed a payload in a Word file with a pi, not bat? See, now we're kind of bordering on a completely different topic, and yeah, I'd say that's probably beyond the scope of this stream. Maybe we can talk about, you know, embedding payloads and documents in a different stream. But yeah, for now I think I'll skip on that. If we can keep the focus on sort of the content of the stream, that'd be really good. Sorry, mate. All right, so what I'm going to do is I'm going to end it there and say thanks very much. Really appreciate those people who have spent time having a look at what I've been doing, and if you have any questions or concerns or feedback, I'm very open to it, and you know, I appreciate your time. So thank you very much, and good night.